we started talking about reactions. Let us continue and know a few aspects about various reactions. We start with first of all the relation between the G and A. This is well known, but still I thought it is better we look at it once carefully before we go ahead. If you look at basically the expression dG is VdP minus SdT, this is what we all know, am I right? So in principle at constant temperature this turns out to be nothing but VdP. So at constant temperature this is dG is VdP. And if we assume that there are gases involved in the reaction, we can use the ideal gas relation and where RT equal to PV, and then use this V in terms of RT and P and write V equal to RT by P. Once we write that, we can write the dG as RT dP by P. RT dP by P is RT d ln P. So that is how you actually get this expression. And in this now if I simply look at two pressures, let us say, I can say dG 1 can be written as RT d ln P1. I can write another dG2 as RT ln d ln P2, or if we can write it in terms of G alone, you can simply even not write this, simply write G equal to RT ln P. The D can be removed. So and once you write it, you can write G1 equal to RT ln P1 and G2 equal to RT ln P2. So whenever you want to look at differences in the free energy at various pressures, you can simply take as G2 minus G1 is equal to RT ln P2 by P1. So I can simply write G2 minus G1 is equal to RT ln P2 by P1. So like this we can simply look at how the free energies change as a function of pressures, and if one of them, let us say P1 is a standard pressure. What is the standard pressure for us? Atmospheric pressure. So if I take it as atmospheric pressure, I can write it as G minus G naught. I will take G1 as related to atmospheric pressure, can be written as RT ln P, because if P1 is equal to 1, if I take P1 as 1, then P1 goes off in this equation. So you can write G2 minus the G1, I will call it as standard free energy at atmospheric pressure. So that I will refer it to as G naught. So we always refer free energy at atmospheric pressure as G naught. So I can write G minus G naught is equal to RT ln P. And the same thing if you are talking in terms of activities, I can write the same thing as RT ln A. If we are talking of a mixtures of it, in fact there also if you are talking of a mixture of gases, you can write G I minus G naught I can be written as RT ln Pi for a particular gas. If there are mixture of a number of gases, for a particular gas we can write ith gas, you can always write this expression. So this is how we can express the free energy changes in terms of activities. And once we know this, we can start looking at various equations, various reactions that take place, and look at how we can correlate the free energies with the activities, and then from that get to know information about whether the reaction will go in the forward direction, whether the reaction will go in the backward direction. All this can be accumulated once we are aware of it. So you can see, starting from a simple Maxwell's equation, which is dg is vdp minus sdt, and this I hope all of you know how we derive it. I will not need to derive it. So we are simply assuming the temperature to be constant, and from there we have arrived at this for a given atmospheric pressure, one pressure being atmospheric pressure, and from there we have come to the activity. Now let us look at a equation, a reaction where let us say A is reacting with B and giving you C plus D, and here to make it more specific, we will call it as some A moles of A is reacting with B moles of B to give you C moles of C and D moles of D. Okay? And you can see this kind of reactions, variety of reactions where certain number of moles of a particular component are involved in the reactions. For example, if you take Mg, simple example, magnesium plus oxygen gives you MgO. When we say, when you need to balance the equation, you need to see 2 moles of magnesium would give you 2 moles of MgO with 1 mole of oxygen. So that these numbers are the numbers that we are talking here. When I say small a b c d refer to those moles, and if that is the case, then the free energy change for such a reaction is nothing but the free energy of the products minus the free energy of the reactants. Am I right? So I can say the G of the reaction is nothing but I can write it as C into G of C plus D into G of D minus I can write A into G of A plus B into G of B. This is the reactants, this is the products. This is the free energy of C plus the free energy of D minus the free energy of A and free energy of. Okay. I can also write the same thing at a standard state. Sorry, I will put not on the top. That means at atmospheric pressure, if this reaction is happening, then I can write it as C into G C naught plus D into G D naught minus A into G A naught plus B into G B naught. Everything remains the same excepting that we are talking at a standard state. So if that is the case, now I can write G minus G naught. For example, this is actually delta G, change in the reaction, okay, change in the free energy. So I should not put G, I should put delta G naught. So delta G is this, delta G naught at the change in the free energy for the reaction at the standard state, standard conditions is this. If I take the difference of these two, difference of these two is basically nothing but the difference of these two. So I can write C into G C minus G naught C, am I right, plus D into G D minus G naught D minus of whatever it is. If you want more specific, we will write A into G A minus G naught A plus B into G B minus G naught B. Here if you look at this part is nothing but this. We already know that G minus G naught is RT ln A. So, I can write this as C into RT ln A of C, correct, activity of component C, and then plus D into RT ln A of D minus A into RT ln A of A plus B into RT ln A of B. Basically, now we have got the whole free energy change in terms of activities. Am I right? Any confusions? We simply looked at the free energy change of the reaction, we took it as products minus reactants, and then we looked at the same free energy change at the standard state, and the difference between the two brings out that there is a component which is the free energy in a at any given condition minus the free energy in the standard state, and this difference is always RT ln A. And so, from this I can write that delta G minus delta G naught is RT ln A of C to the power C into A of D to the power D divided by A of A to the power A and A of B to the power B. Are we right? Because these are ln's, so we can take the ln out and then do multiplication. So, here basically you are simply multiplying, and because this is negative, it comes to the denominator, positive is in the numerator. So, this particular thing is what we call it as this, the bracketed item is what we call it as K, equilibrium constant, and we learn a lot of things from this. As we go along, we will see how does this influence the whole reaction, and this the whole reaction, whether it will go in the forward direction or the backward direction, always depends on that. So, I can write this as RT ln K, and delta G here, if this reaction is taking place if under equilibrium conditions, if there is equilibrium that is established between the reactants and the products, then this delta G is 0. Whenever there is an equilibrium between anything, we have seen liquid to solid transformation, delta G is 0. So, the same argument I can hold even for magnesium plus oxygen reacting to give you MgO. The change in free energy for such a reaction should be 0 if all the three components, whether it is the products and the reactants, if everything is under equilibrium, then the delta G is 0, and if that is the case, then you can say that delta G naught is minus of RT ln K, because there is a minus there that comes here. This is a very, very crucial equation which will tell you that we can correlate change in the free energy of a reaction in a standard state to the equilibrium constant, which is nothing but activities of various components, and this is how we will be able to see how to understand reactions. And maybe I will just take one or two examples just to give you whatever we have done so far. Is it clear? So, you can see for example, let us take any example. Okay, I will take an example. Let us say you are melting steel in a magnesia crucible. At some temperature 1600 degrees centigrade or so. You want to know whether this magnesia crucible will be intact at the temperature or will it dissociate into magnesium plus oxygen. If it dissociates, obviously you cannot melt the steel in that crucible, it is no more stable. So, if you want to melt anything in a crucible, that crucible material should be stable at that temperature. So, if that is the case, how do I find out that? Simply what you do is find out what is the reaction that goes on. Mg plus O2 gives you MgO. So, 2 Mg plus O2 should give you 2 MgO. If this is the case, then find out what is the delta G naught for this reaction. If the delta G naught for the reaction is available, usually delta G naught is given in the form of A plus Bt. Whenever you look at various, why it is written in the form of A plus Bt is basically because delta G naught is delta H minus T into delta S. So, whether the B is negative or positive, let us not bother about it. Okay. So, basically because it is delta H minus T into delta S, so you would always see the expression for the delta G naught is always given in form of two constants and linear dependence on temperature. Once you know the A and B terms for that particular reaction, which are available based on, basically people have done such reactions at various temperatures and found out how the free energy is changing. How do you find out the free energy change for a reaction? From Cp change. Anything else? Look at particularly the thing that is easily measurable for any reaction is the enthalpy change, because that is something you can measure using a calorimeter. So, measure the enthalpy change at various temperatures for a reaction, and once you measure the enthalpy changes at various temperatures for a reaction, from that you can actually get how the, and keep the pressure constant, because we are all talking of delta G naught there. At atmospheric pressure, do this reaction at various temperatures, measure how the delta G H is changing, and from that you can actually get this. In fact, people have done this and for various reactions, and these values are standard values are available. If you go to any standard handbooks on thermodynamics, you will see for various reactions what is this in terms of temperature is available, what are these, particularly what are the AB values for various oxidation reactions, various reactions where sulfides form, okay, sulfates form, and such reactions they are all tabulated. You go to any thermodynamics handbook, you will see it. For example, one of the good ones is what is called Kubaszewski. If you go to this particular book, it is thermochemistry, a book on thermochemistry, which gives you towards the end so many appendices, and each appendix gives about various such reactions, what is the values of A and B. Once I know this, A itself is a function of temperature, you mean? No, A and B are constants. I mean, if they are function of temperature, then obviously this function becomes more complicated. So, A and B are usually fixed, because that is how, okay, in principle if you go a little detailed, okay, if you think these two are nothing but delta H minus T into delta S, these two are also functions of temperatures. In principle, yes, but for in such a case this whole expression becomes a little complicated expressions, where in each of them you will get temperature dependence. But to a large extent people have seen that A and B are constants for most of the reactions. Okay. So, you simply take A and B as constants and do it, and that works out for most of the reactions. Yeah, why are, you see, the question is, if this magnesia crucible at that temperature, will it dissociate? That is what we are interested in. You know, at any temperature, whether the reaction will go in this direction or whether the reaction will go in this direction, we do not know. What does it depend on? Whether the reaction will go in this direction or in this direction depends on what is called partial pressure of oxygen. Okay. For this reaction there is a equilibrium partial pressure. How do I calculate the equilibrium partial pressure? Simply find out what is the K. So, I know K of this reaction, I can write it as activity of MgO square divided by activity of magnesium square into partial pressure of oxygen. In case of gases we call yes, MgO giving you Mg plus O2. We are trying to find out whether that will happen or not. Correct. The point is at that particular temperature and pressure that we have, whether this will happen or not. For example, this melting is taking place in a furnace, let us say, where there is certain oxygen partial pressure. My furnace is under certain oxygen partial pressure. Now, for that oxygen partial pressure which is available in the furnace, whether this reaction will happen or not, whether the MgO will dissociate or whether the MgO is stable. How will I know? If I know what is the partial pressure of equilibrium partial pressure of oxygen for this reaction at that temperature. For example, if I know the delta G naught as a function of temperature, by putting 1600 degrees centigrade into it, mind it, you should remember that whenever we are talking of any thermodynamics we talk of temperature in Kelvin. So, convert it into Kelvin, put it into this, so you will know delta G naught, and delta G naught we know is nothing but minus RT ln K. So, from once I know delta G naught I will know K, and once I know K I will know P naught, partial pressure of oxygen, which is the equilibrium partial pressure of oxygen at that temperature, which will keep on changing at different temperatures. So, once I know that, okay, and what is the actual pressure inside the furnace if I know, and if the actual pressure of oxygen is higher than the equilibrium partial pressure of oxygen, then what would happen? Reaction should happen in the forward direction. Whenever oxygen content is more, okay, the Mg should get oxidized and it should go in this direction. If the oxygen content inside the furnace is lower than what is the PO2 of the reaction, then what happens is the system would go in such a way that oxygen is created in the process, so that it maintains the oxygen partial pressure inside the furnace equivalent to the equilibrium oxygen pressure partial pressure. So, if the actual oxygen partial pressure inside let us say you are doing this in vacuum, let us say at 10 to the power minus 4 torr. So, if the melting is taking place in vacuum and then you find out what is the PO2 for that reaction at this temperature, in fact if you do it, what you would get is that partial pressure of oxygen will be actually 10 to the power minus 22. You will get as 10 to the power minus 22 or minus 23 it comes out. So, this value is much smaller than this. As a result, at this particular vacuum level, at this particular pressure level, because the actual oxygen partial pressure is much larger than the equilibrium partial pressure of oxygen, the reaction would not go in this direction, would go in this direction, because oxygen, excess oxygen is available than the oxygen partial pressure of the reaction. If the oxygen that is available is less than the partial pressure of oxygen that is required to maintain the equilibrium, then what happens is MgO will dissociate and will give you oxygen by the way, so that this oxygen joins the atmosphere to maintain the equilibrium. So, this is how I can simply calculate what is the partial equilibrium partial pressure and find out what is the actual partial pressure inside the thing, and then find out whether this MgO is stable or not stable. This can be done for any of the things. Whenever you see all meltings are done in certain crucibles, whether it is alumina crucible or silicon carbide crucible or whatever kind of crucibles. So, you need to make sure that these crucibles are stable, particularly when I am why I have to be bothered is whenever I am doing melting in vacuum. Vacuum means lower pressure. Whenever the pressure is low, okay, the volume has to be high, P and V are inversely proportional. So as a result the reaction will go in such a direction which will increase the volume of the system. So what can increase the volume of system if the oxygen can come out. So as a result there is always a tendency whenever I am melting material in vacuum, the oxide which is there in the crucible may dissociate to give you oxygen, provided that particular pressure in the furnace is smaller than the oxygen partial pressure under equilibrium conditions. Only if it is smaller than, and if it is larger than, then it will not happen. Okay. So this is one such example. We can think of many such examples. Let us say you are trying to anneal copper in a atmosphere which is containing hydrogen and H2O. Most of the time annealing is always done in furnaces which are actually heated by various oils. So where there is always hydrocarbons, these hydrocarbons will break and give you some hydrogen, and some moisture is also expected in the reaction. So there is what is called a partial pressure of pH2 by pH2O. If I know what is the actual pH2 by pH2O that is being maintained in the furnace, one can do what is called mass spectroscopy and things like that to measure the actual partial pressures of oxygen, various gases in any furnace atmosphere, and if I can measure and find out what is the actual value inside the furnace. Now I would like to know whether this copper which is being annealed in that furnace is going to get oxidized or not. How do I know that? To know that, first of all, look at the copper oxidation reaction. This is Cu2O. Okay. So that means basically 4 copper plus 2 oxygen should give you 2 Cu2O, and the other reaction that is possible is H2 plus O2 giving H2O. Again you do this. Now look at a combination of these two reactions. If you subtract this 2, and you can say that 4 Cu plus 2 H2O will give you 2 Cu2O plus 2 H2. Am I right? Basically oxygen goes off, this is minus, I have taken it that side, this minus I have brought it this side simply. So that means copper, H2O can oxidize copper and to give you Cu2O, and H2 can reduce copper oxide to give you Cu. What does that depend on? It depends on what is the actual values of Cu, H2 and partial pressures of H2 and H2O. So if you look at the equilibrium constant for this, for example, if I know the free energy change for this reaction delta G naught for this reaction, and I also know the delta G naught for this reaction, let us say as a function of A plus Bt kind of thing. If I know that by adding those two or subtracting one from the other, I will be able to know the delta G naught for this reaction. And because you can see there are 4 moles and 2 moles in both the sides, I can actually make it simplified. 2 Cu plus H2O gives you Cu2O plus H2. Whenever I am dividing with 2, obviously the delta G of the reaction also has to be divided with 2, this has to be kept in mind. So whatever delta G naught I am getting by subtracting delta G naught of this minus the delta G naught of that, okay, has to be divided by 2, so that you know the free energy change for this particular reaction. And for that reaction, if I now want to write down what is K, K is nothing but now activity of Cu2O into partial pressure of hydrogen divided by activity of Cu square and partial pressure of H2O. And if we assume that this reaction is giving you a pure copper oxide and a pure copper is getting oxidized in this particular condition, there are no impurities in that, then whenever it is pure the activity is equal to 1. So, there is no second component. Whenever there is a second component, then we have to consider what is the activity of it. So, activity basically becomes 1 when it is a pure component. So, if pure copper is getting oxidized and giving you pure Cu2O, then the activities are 1s for these two, then I can write K as nothing but P of H2 minus P of H2O. So, I can find out, if I know the delta G of this reaction, what is the equilibrium partial pressure ratio of H2 to H2O. This can be easily found out once I know the delta G naught, and simply I will put this equation, and from that I can find out K, and K is nothing but this. So, I will know the what is the equilibrium, and once I know what is the actual value of pH2 by pH2O in the furnace, and if that actual value of pH2 by pH2O is greater than this value, then what does it mean? I have an excess hydrogen in the furnace. When I say the actual pH2 by pH2O is greater than pH2 by pH2O, remember always use partial pressure as small p of the standard state. If this is higher than this, then that means you have excess hydrogen inside the furnace than what is there for the standard reaction. If there is excess hydrogen, then that means what? The reaction will go in this direction. If this value is smaller than this, then the reaction will go in that direction. That means copper will get oxidized. So, this is very, very important whenever you are doing annealing. For example, steel, you want to do hot rolling of steel. Before hot rolling of steel, you have to heat the steel at 900 degrees or 1000 degrees centigrade for some time before you start rolling it, and you do not want this whole steel to get oxidized at that temperature. Okay? So, if that is the case, you need to know what is the partial pressure of H2 by H2O that I should maintain inside the furnace, so that the steel does not get oxidized. So, you can see that all this the actual practical applications of the thermodynamics come when you want to use simply hydrogen annealing of copper, or hot rolling of any of the steels or whatever it is, aluminum alloys that you are talking about. So, all is related to the presence of this. Of course, depending on the actual equation, if I am talking of Fe, then I have to actually see what is the type of oxide that is forming, is it FeO or Fe2O3 or Fe3O4, and accordingly the actual numbers will change a little bit, and then so here also the values will be slightly different. Otherwise you will see that, but as long as the gas molecules are not changing, then this whole thing will not change, because we are not bothered about what is the metal and the oxide much, because we are assuming that they are, but then this may not be always true for alloys. For example, if I am looking at steel, steel is not pure iron. So, I need to consider, when I say activity of iron there, I need to find out how much of iron is there in the steel. Of course, luckily for a plain carbon steel, we are talking of a mild steel, let us say it is about 0.2% carbon. So, it is more or less can be treated as a pure iron. So, activity of iron actually is 0.9998. If you are considering steel containing 0.2% carbon, the activity of carbon is accordingly the value 0.0002, and activity of iron will be 0.9998 if it is a binary alloy. So, if it is a multi component alloy, if it is a stainless steel that I am talking about, then accordingly I have to consider what is the activity of. So, the actual activities that we are talking here, which we are equating it to 1, this would not be true if I am considering alloys. If I am talking of a let us say a superalloy where there are various elements present, and I need to look at let us say oxidation of each of the alloying element, I need to consider what is the, for example, in a superalloy, again superalloy also I am heat treating at certain temperature to do hot rolling of superalloy. Let us say I want to find out whether nickel of that superalloy will oxidize, whether aluminum of that superalloy will oxidize or not. If you want to find out, you have to actually find out for each of them equations like this, and the activities of the oxide and the metal that you are putting in this equation should be accordingly the compositions of those. Once I know the composition of it, mole fraction of it, activity is equal to, and again this issue activity equal to mole fraction also is not so easy. When is activity equal to mole fraction? When it is an ideal solution. So, if I am assuming it to be an ideal solution, and ideal solution works out only when in a very dilute conditions, whenever it is a very dilute alloy, then I can think of that. But if I have alloying elements of the order of 20-30%, then ideal solution may not work out. So, that is where you have to consider then activity is activity coefficient into the mole fraction. So, all these complications will come into picture when you are talking about materials where you do not have pure components. So, as long as pure components are there, these equations turn out to be very easy. Okay. So, you can see like this we can talk about many examples where this kind of knowledge of the equilibrium constant and the knowledge of our basic equation with which we have started, take dg equal to vdp minus sdt, and this time let us assume that we are doing at atmospheric pressure. The whole reaction is happening at atmospheric pressure, then obviously dp becomes 0, pressure is constant. So, I can write dg is equal to minus sdt, and I can write d of delta g is equal to delta s into dt, and for a standard thing I can write it as delta d delta g naught is equal to minus delta s naught into dt, and we can always write the delta g naught as delta h naught minus t into delta s naught. Am I right? If that is the case, then I can reframe this equation and then say that delta s naught is equal to delta h naught minus delta g naught divided by t. Simply rearrange the things and I put that into that equation, and then I can say that d of delta g naught is equal to minus of delta h naught minus delta g naught by t into dt. Am I right? Simply in the place of delta s naught I am putting this, and if I am putting that, then we can write again as so you can see that T, if it comes this side, is T into d of delta g naught minus delta g naught. We have brought both the delta g naughts one side so that we can actually differentiate them very easily, and minus delta H naught by T. If you divide this whole thing by T square, delta G naught dt, you are right, perfect, dt has to come there, otherwise you cannot differentiate, it has to come there. Okay. So if you divide with the T square on both the sides, you will be able to see this whole thing as dou of delta G naught by T of dou of 1 by T is equal to actually delta H naught. You can actually show that to become actually this. Basically this becomes a dg by T and dg by T square, and that if you take it as 1 by T, it turns out to be this. You can do this exercise, and what comes out of this is, because we know delta G naught is actually minus RT ln K, if you put that into that, you will see that dou delta R ln K by dou of 1 by T is equal to delta H naught minus, and in principle this R can be brought out and R can come out here. So you can see that dou of ln K by dou 1 by T, that means if I have the K values, what is called the equilibrium coefficient values, as a function of temperature, and if I plot the ln K, if I plot ln K as a function of 1 by T, I should be able to get a straight line where the slope is delta H naught by R, where the delta H naught is the heat of the reaction. So one can find out the heat of the reaction, and the K and 1 by T are related by the heat of the reaction. This is similar to almost like a Kissinger plot and things like that, that we talked about it in the last class. So any activation energy, more or less we do the same thing. So you can see the equilibrium constant is related to the temperature through the delta H of the reaction. So that means in principle equilibrium constant is not constant, okay, though we use the word equilibrium constant. So it is it's a fixed value for equilibrium at certain temperature, but as a function of temperature, if the same reaction is occurring at different temperatures at the same pressure being constant, you will be able to see that this follows such a thing. Of course it depends on how accurate your measurements are to see whether this will be a good fit or not a good fit, depends on your actual measurements, and as long as the measurements are right, this gives you a good fit. If I do it at let us say 4 different temperatures and find out what is the K at all these 4 different temperatures, how do I find out what is the K? Basically I find out delta G naught at various temperatures, at different temperatures find out the delta G naught, and once I know the delta G naught, from that I can find out the K and plot that K with 1 by T. So if you have 3 or 4 points, in principle you can plot a straight line, and as long as the data is reliable you will get a good straight line, because the equation, there is nothing wrong in the equation. If all the points are not falling on the straight line, that means only your delta G naught measurements are wrong, because if the delta G naught measurements at various temperatures are wrong, then the K that you get out of it will be wrong, and if that is wrong you will not see a good fit. That is why we always, whenever you talk of a fit like that in any statistical, we talk of what is called the confidence levels. So whether the R square value of the fit, whenever the R square value of the fit is at least more than 95%, that is when we say that actually the fit is good. So that again depends on how reliable all these k values, and once you have this, one can find out this k, and from that we will be able to find out at various temperatures how the reactions take place. So your point that actually delta H and delta S are related to temperature actually comes here, because k is related to delta G naught and k itself is a function of temperature. That comes basically because delta G is a function of temperature. Okay. So I think with this we will stop. If you have any queries, feel free. We will again have one more class where we will see a few more reactions and look at what is called an Ellingham diagrams, okay, where we are actually going to talk about various stabilities of various oxides, okay, which oxide is more stable than the other oxide, and if one oxide is more stable than another oxide, in principle we may be able to reduce one oxide with a metal. For example, if you take a example of very standard example everybody knows, if I take FeO or Fe2O3 plus aluminum, you should be able to get Al2O3 plus Fe. Whether this reaction will go in this direction or not depends on whether the delta G naught of this reaction is negative or not at a given temperature. At a given temperature, if the delta G is negative, what is delta G naught? It is the free energy of the products minus the free energy of the reactants. So if the free energy of the products is smaller than the free energy of the reactants, then only delta G naught will be smaller, okay, will be negative, and if that be the case, that means the products have a lower free energy than the reactants. It is like a liquid going to a solid, it happens only when the solid has a lower free energy than the liquid. So you can see such reactions happening, and for that what you need to do is basically find out what is the free energy of aluminum getting oxidized to Al2O3 and what is the free energy of iron getting oxidized to Fe2O3, and then find out a combination of these two reactions by, if I do this negative, so I will know aluminum plus Fe2O3 will give you Fe plus Al2O3. So I have the delta G naught of this reaction, I have the delta G naught of this reaction, I will be able to find out the delta G naught of this reaction at a particular temperature, and at that temperature if this turns out to be negative, then I can say yes, this reaction would happen. If this turns out to be positive, then actually the reverse will happen. So whether these reactions are such reactions are feasible, if that is feasible, then what is called metallothermic reductions are possible. Even for that matter, if we want in a blast furnace iron oxide to be reduced by carbon, that reaction of iron oxide plus carbon should give you the iron plus carbon dioxide, that reaction should be negative. If the delta G is not negative, you will not see that reaction happening. Similarly, if you want iron oxide to be reduced by carbon monoxide to give you carbon dioxide plus iron, again that reaction also should have negative. Again there also you can simply find out the reaction of iron plus oxygen, carbon plus oxygen reaction, add the two reactions, then you will get iron plus carbon monoxide giving you carbon dioxide plus iron, iron oxide plus carbon monoxide giving you carbon dioxide plus iron, or iron oxide plus carbon giving you carbon monoxide or carbon dioxide plus iron. So you can add such reactions. That is one good thing about all these reactions, is that you can simply sum them up, and the free energy being extrinsic property, you can simply sum them up, okay. So you can sum them up and get the actual values, and if the actual value becomes negative at a particular pressure and temperature, we are already talking about at a fixed pressure, because we are talking of delta G naught and temperature, at a given temperature we do this, okay. We will stop here.